Put your understanding of time-variant sine functions to the test by solving for the following values. Be cautious, because I've hidden a couple tough ones in here that might take some thought and effort. Example 1 has a frequency of 60 Hz, a peak voltage of 169.7 volts, and we're being asked to determine the output voltage at 2.2 milliseconds. Example 2 has a period of 12 milliseconds, a peak voltage of 59.4 volts, and we're being asked to determine the voltage at 8 milliseconds. Example 3 has a frequency of 150 Hz, an effective or RMS voltage of 24 volts. Note the dramatic emphasis I'm using, and we're being asked to determine the voltage at 1.3 milliseconds. Finally, example 4 has a frequency of 1.2 kHz, a peak-to-peak voltage of 70.5 volts, and we're being asked to determine the voltage at 1.5 milliseconds. By the way, it should go without stating that it's necessary to derive the formula for voltage as a function of time prior to solving for the voltage at specific times for each example problem. By all means, pause the lecture and give this your best shot. If you're tracking, you should have obtained the following values. For the first example problem, we're given a peak value of 169.7 volts and a frequency of 60 Hz. Our time-variant sine wave function resolves itself into 169.7 volts times the sine of 360 times 60 times the time of interest. Substituting in 2.2 milliseconds, the expression in parentheses yields an angle of approximately 47.5 degrees. Sine of 47.5 degrees is approximately 0.7375, and multiplying this by the peak value of 169.7 volts yields approximately 125.2 volts. For the second example problem, we're being given a peak value of 59.4 volts and a period of 12 milliseconds. A period of 12 milliseconds is equal to a frequency of approximately 83.3 Hz. Our time-variant sine wave function resolves itself into 59.4 volts times the sine of 360 times 83.3 times the time of interest. Substituting 8 milliseconds, the expression in the parentheses yields an angle of 240 degrees. The sine of 240 degrees is approximately negative 0.8660, and multiplying this times a peak value of 59.4 volts yields approximately negative 51.4 volts. For the third example problem, we're given an effective or RMS value of 24 volts. This is equivalent to a peak value of square root 2 times 24 volts, or approximately 33.9 volts. Hopefully you didn't fall into this trap. Peak values are always greater than effective values. Additionally, we're given a frequency of 150 Hz. Our time-variant sine function resolves itself into 33.9 volts times the sine of 360 times 150 times the time of interest. Substituting in 1.3 milliseconds, the expression in parentheses yields an angle of 70.2 degrees. Sine of 70.2 degrees is approximately 0.9409, and multiplying this times the peak value of 33.9 volts yields an output voltage of approximately 31.9 volts. For the fourth example problem, we're given a peak-to-peak value of 70.5 volts and a frequency of 1.2 kHz. Given peak-to-peak is 2 times peak, this waveform has a peak value of half that, or 35.25 volts. Again, hopefully you didn't fall into this easy trap. Our time-variant voltage function resolves itself into 35.25 volts times the sine of 360 times 1200 times the time of interest. Substituting in 1.5 milliseconds, the expression in parentheses yields an angle of 648 degrees. What does this mean? It means exactly what you think it does. Given such a high frequency of 1.2 kHz, 1.5 milliseconds into it will result in more than one complete revolution around the 360-degree circle. Think about it. Something operating at 1.2 kHz has a period of only approximately 833.3 microseconds, or roughly 0.8333 milliseconds. Substituting 1.5 milliseconds into our analysis means that the waveform is peaked and valleyed and peaked again, and is in the process of climbing out of yet another valley at 648 degrees minus 360 degrees, or 288 degrees. Regardless, sine of 648 or 288 is approximately negative 0.9511, and multiplying this times the peak value of 35.25 volts yields an output voltage of approximately negative 33.5 volts. Let's come at the concept of period and frequency from a different perspective. Given these plots of sinusoidal voltage as a function of time, see if you can determine the peak value, the peak-to-peak value, the RMS or effective value, the period, and the frequency, as well as express these sinusoidally variant voltage waveforms as functions of time. Our first example in red looks like it has a peak value of 20 volts. This is equivalent to a peak-to-peak value of 40 volts. This means the red waveform has an effective value of approximately 14.1 volts. Again, the effective value is always less than the peak, and the peak is always greater than the RMS value. The time span between zero crossings going positive looks to be 13 milliseconds. A period of 13 milliseconds is equivalent to a frequency of roughly 76.9 Hz. When we express voltage as a function of time, we arrive at the expression V1 of t equals 20 volts times the sine of 360 times 76.9 times the time of interest. Given the relationship between peak value and effective or RMS value, one might also see this expression written as V1 of t equal to the square root of 2 times 14.1 volts times the sine of 360 times 76.9 times the time of interest, making it exceedingly obvious this waveform has an effective value of roughly 14.1 volts. See if you can perform the exact same procedure for the waveform in yellow. By all means, pause the lecture and take your best shot. If you're tracking, you should have obtained the following answers. The second example in yellow looks like it has a peak value of 22 volts. This is equivalent to a peak-to-peak value of 44 volts and an effective value of approximately 15.6 volts. The time span between the zero crossings going positive looks to be 9 milliseconds. A period of 9 milliseconds is equivalent to a frequency of roughly 111.1 Hz. When we express the sinusoidally variant voltage waveform as a function of time, we arrive at the expression V2 of t equals 22 volts times the sine of 360 times 111.1 times the time of interest. As previously, given the relationship between peak and effective or RMS value, one might also see this expression written as V2 of t equals the square root of 2 times 15.6 volts times the sine of 360 times 111.1 times the time of interest, making it exceedingly obvious this waveform has an effective value of roughly 15.6 volts. Note if we were to display the first and second waveform on the same plot using the same vertical and horizontal scale, note the red waveform's period is longer, corresponding to a lower frequency, and the yellow waveform's period is shorter, corresponding to a higher frequency. As a result, the yellow waveform with a higher frequency and smaller period can fit more cycles into the same time span than can the red waveform. It makes sense. Since we've got both expressions right in front of us, we should be able to solve for voltage at specific times. Let's say we're interested in the voltage differential between the red and yellow waveform at 16 milliseconds. Substituting a time of 16 milliseconds into each equation results in the red waveform having a value of approximately positive 19.9 volts, and the yellow waveform having a value of approximately negative 21.7 volts. It can be therefore said that at 16 milliseconds, the red waveform is positive 19.9 volts minus 21.7 volts, or approximately 41.5 volts higher than the yellow waveform. The point being that when calculating differential between two sinusoidal waveforms with differing magnitude, frequency, and/or phase shift, one can at times arrive at differentials exceeding either individual waveform's peak value. Similarly, there exist moments in time when these waveforms briefly equal each other such that no differential exists. Notably here, 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 and here. Alright, that about wraps up this quick lecture on period and frequency. In conclusion, this lecture examined period and frequency of sine wave functions. We learned to calculate period and frequency numerically and graphically, as well as evaluate sinusoidal functions with respect to time. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.